students, our next topic is linear restoring force and simple harmonic motion. In the mid-17th century, Robert Hooke was a scientist who discovered that the extension of a spring is proportional to the applied force for both positive and negative displacements. Again, the extension of a spring is proportional to the applied force, both for positive and negative displacements. The force Fs, the spring force exerted by a spring, is given by Hooke's law. In response to its name, this law is called the Hooke's law. It is defined as Fs is equal to minus k into x minus x0, where k is a constant of proportionality called the spring constant. That means Fs is directly proportional to the displacement. x0 is the equilibrium position and it is the x minus x0 is the displacement of the end of the spring from its equilibrium position x0. So this extension of a spring is directly proportional to the applied force. Okay, this is called Hooke's law. Now the important features of Hooke's law are the force varies linearly with the displacement. When F increases, displacement also increases, and that it is always directed towards the equilibrium position. That means if the spring is stretched, that is when x is greater than x0, see the figure, this is our equilibrium position, and if it is extended beyond, or the spring if it is stretched to a greater position x greater than x0, this is the applied force in this direction and x is positive, then the spring force will be acting opposite to it in the negative direction. That is Fs is less than 0. So that when the spring is stretched x greater than x0, Fs is negative, directed towards x0. Now the second case is when the spring is compressed. This is the equilibrium position and it is compressed. So this is the direction of applied force. So opposite to it will be acting the spring force Fs. So that Fs is greater than 0 or positive. That is when the spring is compressed, x is less than x0 and Fs is positive, once again directed towards x0. That means the force varies linearly with the displacement and it is always directed towards the equilibrium position. For this reason, Hooke's law force is sometimes called linear restoring force. This is a restoring force which helps the system into its equilibrium position. So this is a variation. R0 is the equilibrium distance between any two particles. At that point, force is 0, and above that value up to R2 there is an attractive force and below that there is a repulsive force. So in this region, Hooke's law is valid, for which force is directly proportional to R, or the distance between them. Okay. Now simple harmonic motion. The motion of the mass on a spring that is displaced from its equilibrium and released is called simple harmonic motion. So this motion, the motion of the mass connected to a spring after it's displaced and released, that motion is called simple harmonic motion. You have to derive the equation for simple harmonic motion considering the block of mass m attached to one end of the spring and the other end is fixed. Okay, we have to find out the equation of simple harmonic motion. Now the block rests on the horizontal frictionless surface. So we have the equation of motion as F is equal to minus k into x minus x0. Take the x0 position as 0. Okay, it lies in the 0 of the coordinate system. So x0 is 0. So F is given by m d square x by dt square is equal to minus kx. So on rearranging you get d square x by dt square plus k by mx is equal to 0. Introducing a variable omega is equal to root k by m, we get an equation in the standard form as d square x by dt square plus omega square x is equal to 0. This is the equation for simple harmonic motion. And any system that obeys this equation is called a harmonic oscillator. Now the displacement and the acceleration are always opposite in signs. As the mass heads towards x greater than 0, the negative acceleration eventually brings the mass to rest and accelerates it back towards the equilibrium position. Now after the mass speeds through the equilibrium position, the acceleration changes sign and the mass is pulled back. We therefore expect the mass to oscillate above the equilibrium position. That is why it is called a harmonic oscillator. Now the solution of this differential equation is x is equal to a sin omega t plus b cos omega t. A and b are constants, or we can write it in another way as c sin omega t plus phi, where c cos phi, when we expand it, c cos phi is a and c sin phi is b. Okay, so it is a sin omega t plus b cos omega t. And the relation between a, b and c are c is equal to root of a square plus b square and phi, tan phi is equal to b by a. Okay. Now this is the variation or the graph between x and omega t. So this is the variation. It is a harmonically varying term x with omega t, and this is called the time period. The motion is periodic in time, going through one cycle in time t is given by omega t, that is equal to 2 pi, and this t is known as period of motion. It is not tension, it is the period of motion, and omega is called the angular frequency of motion, and the maximum excursion or the maximum displacement, which is called this is the maximum displacement, which is called the amplitude of motion, and phi is called the phase angle. It is the initial phase angle phi. Now, some fundamental properties of simple harmonic motion is that frequency of the motion and period does not depend on the amplitude. Now, if the spring is stretched further before releasing the mass, the amplitude of motion increases, which means that mass travels further during each cycle. However, because the force also increases with amplitude, the acceleration increases and the mass moves faster as it passes through the origin. The effect of larger distances is compensated by the effect of higher oscillation, and the time for complete cycle remains a constant in the case. Always in any simple harmonic system, time for complete cycle remains a constant due to this fact. Okay. Now, another important point is that unit of frequency, it is cycles per second, or it is sometimes called the circular frequency hertz. This one cycle per second is called 1 hertz. Okay. Circular frequency is denoted by the symbol F or nu. The natural unit of angle is radian. Okay. So natural unit of frequency is sometimes called the angular frequency, or the unit is radian per second. So angular frequency is often denoted by omega, which has no special name. Its unit has no special name. Both the circular and angular frequency both have same physical dimension, t raised to -1. For both circular frequency or simply frequency or the angular frequency, both have same dimension, but the two quantities differ by a factor 2 pi. That is, omega is equal to 2 pi times the circular frequency. The angular frequency is 2 pi times the circular frequency. So there is a difference between them, even though there is no difference between their dimensions.